Now, continuing our study of sequences, we're going to look at more abstract properties of sequences. Starting with a series of definitions. We're going to say that a sequence is increasing if we have the property that an plus 1, a indexed by n plus 1 is greater than an for all n. So what that means is for each term, the next term is bigger. So that's a natural definition for increasing. If we don't have this property for all n, but only for all n greater than some fixed value, we're going to call that eventually increasing, because that means that maybe the values of the sequence go up and down for a little while, but after a certain point, they keep increasing. A weaker property is to be non-decreasing, which is simply that we have the large inequality. In other words, an plus 1 is not less than an for all n. And if we have it again only for all n large enough, we're going to call that eventually non-decreasing. We have the dual properties of being decreasing, which means that an plus 1 is less than an for all n. And if we have this inequality only for all n greater or equal to a certain value, we're going to call that eventually decreasing. And we have the corresponding weaker property of non-increasing if an plus 1 is not greater than an for all n, and eventually non-increasing if we have it only for n large enough. We're going to call a sequence eventually monotonic if it is either eventually non-decreasing or eventually non-increasing, and monotonic if it is non-decreasing or non-increasing. So let's look at example. The sequence n, so 1, 2, 3, 4, 5, and so on, is of course increasing, and in particular non-decreasing, and therefore monotonic. The sequence 1 over n is decreasing, right? We start with 1, then 1/2, which is smaller, then 1/3, which is smaller, then 1/4, which is smaller, and so on. So in particular, it's non-increasing, and therefore monotonic. If you take a constant sequence, for instance, a constant sequence 1, it's non-decreasing and non-increasing, but of course it's neither increasing nor decreasing. If you take the sequence -1 to the n, that means it's a sequence that takes a value -1, 1, -1, 1, and keeps alternating between -1 and 1. It is not monotonic because the values alternatively increase and decrease. So continuing with definitions, we're going to say that a sequence is bounded above if there is a fixed number, say capital M, such that all of the terms of the sequence, all of the an's, are bounded above by M. In other words, an is less than or equal to m for all n, so all of the terms of the sequence. We don't have a variant with eventually bounded above, because that wouldn't make sense, because let's say eventually increasing was saying that it's increasing for all but finitely many n, that an plus 1 is greater than an for all but finitely many n's. For bounded, this wouldn't make sense, because if you have a bound that works for all but finitely many n, then you can take the maximum of the finitely many terms that you didn't consider, and then take the maximum of the bound you had, and this maximum of the finitely many terms, and you get what we will call an upper bound for the sequence. Here, an upper bound for the sequence is one of these numbers that works and bounds above all of the terms of the sequence. Of course, when you have one upper bound, anything bigger is another upper bound. So there are many upper bounds. We're going to say that the sequence is bounded below if there is a number b such that bounds below the sequence, that is, an is greater or equal to b for all n. So all of the terms are at least b. And b in this case is a lower bound for the sequence And again, if b is a lower bound, then anything smaller is going to also be a lower bound. So we have many lower bounds. An important property of the real numbers that we're going to admit is that if a sequence is bounded above, it also has a least upper bound. So as I pointed out, once you have one upper bound, anything bigger is also an upper bound. And so it's a natural question whether you can find the smallest upper bound or least upper bound. And indeed you can. We're going to admit it. And dually, if the sequence is bounded below, there is a greatest lower bound. So we'll note that the sequence n, so 1, 2, 3, 4, 5, and so on, is monotonic. Of course, it's increasing, but it's not bounded, because it's not bounded above, because it keeps growing, so there is no fixed number that is going to be bigger than all of n's. The sequence cosine of n pi over 2 is bounded but not monotonic. It's bounded because it takes the value when n is 1, you get cosine pi over 2, which is 0. When it's 2, you get cosine of pi, which is negative 1. When it's 3, you get 0 again. When it's 4, you get 1. And you keep moving from 1 to 0 to negative 1 to 0 to 1. So it keeps going up and down, so it's not monotonic, but it is bounded because it only takes 3 values, 0, 1, and negative 1. So we have seen that if a sequence is bounded above, it has a least upper bound, and if it's bounded below, it has a greatest lower bound. Let's look at some basic properties of this least upper bound and greatest lower bound that are going to be useful for us. One way to denote this least upper bound is by sup of an, because it's a supremum of the sequence. That's an alternative name for the least upper bound. It is the smallest upper bound, so one way to think of it, if m is the smallest upper bound, if you take any smaller number, in other words something that can be written m minus epsilon where epsilon is positive, then it's no longer an upper bound for the sequence, which means that I can find a term in the sequence, let's say a indexed by n epsilon, this term of course depends on epsilon, that is bigger than m minus epsilon. And that means there is a term of the sequence above, in other words m minus epsilon is not an upper bound for the sequence. Similarly, calling inf of an the greatest lower bound, or infimum of an, that's again an alternative name, if L is this greatest lower bound, then because it's a greatest lower bound, that means that anything bigger is no longer a lower bound. So if I add an epsilon to it, then it's no longer a lower bound. That means there is some term of the sequence that is below. So for each epsilon, there is an epsilon with a n epsilon less than L plus epsilon. We'll see that this way of looking at the least upper bound and greatest lower bound will be useful for us to prove some interesting fact about sequences. Now, the key result that we want to discuss in this video is that if a sequence is eventually non-decreasing and bounded above, then it is convergent. And if it is eventually non-increasing and bounded below, then it is convergent. So one way to summarize that is to say that if a sequence is eventually monotonic and bounded, it is convergent. Of course, this is a corollary, but what you have in the rate frame is more general. So let's prove one of them, and of course the other one can be proved the same way, just to justify this. So we start with sequence an that is eventually non-decreasing, which means that for n large enough, greater or equal to some number n0, then we have an plus 1 is not less than an, for each one of these n large enough. And the sequence is bounded above, so that means that in particular there is a least upper bound, let's call that L, that is a real number. And now, because it's a least upper bound, we use the observation we just made that for any positive epsilon, there is some n epsilon greater than n0, with a indexed by n epsilon greater than L minus epsilon. But that means that for n greater than this value, L minus epsilon is less than an epsilon, which is not greater than an, which itself is not greater than L. This inequality is precisely what we just have written, that an epsilon has been picked to be greater than L minus epsilon. This inequality is because for n greater than n epsilon, in particular greater than n0, the sequence is non-decreasing. That means an plus 1 is greater than an for each n, and in particular an is going to be greater or equal to an epsilon. The last inequality follows from the fact that L is the least upper bound. In particular, it is an upper bound, so it is greater or equal to each term of the sequence. So that means that the distance between an and L is less than epsilon, and therefore the limit of the sequence is L, which proves our theorem. So it proves that not only that if the sequence is eventually non-decreasing and bounded above, it is convergent, but it gives us an idea of how to find this this limit. This is going to be the least upper bound of the sequence starting at n0, where the sequence is non-decreasing starting at n0.